We have, so to speak, finished the appetizers, and we are now ready for the main course. And that's what we've been building up to all along. I wanted to re-emphasize, in my experience, a lot of people arrive in this class and they may be a little bit rusty when it comes to polynomial division, particularly the synthetic division. They may be a little bit rusty when it comes to quadratic formula. And so this would be a great time to go onto YouTube or somewhere else and review that material, because we are going to be making heavy use of synthetic division and also quadratic formula from time to time. So very important that you feel comfortable doing that. What are we going to do here? Let's take a look at the example that we're going to start with. You can see now that we're not building up anymore. We're going to be tearing down. So the instructions are saying find all the zeros, real and complex, along with the associated multiplicities. And you can see that we have these very intimidating looking polynomials here. And so there is a reason that we require a graphing calculator for this class, and that is a great way to get started. So I'll tell you what I'm going to do. The very first thing is I'm going to make some space here. Let us graph that first polynomial right there, and we'll see what the graph shows us. There we go. I'm going to clear some stuff here. Let's clear that. So we have 6x to the fourth minus 7x cubed minus 12x squared plus 3x plus 2. And I think that probably a standard zoom is a good starting point. Again, standard zoom is zoom 6. So it's this one right here. Z standard stands for zoom standard. And that's our polynomial. Now, is it absolutely vital we be able to see all the parts on the screen? It's usually not a bad idea. And so for a problem like this, I would usually want to customize the view a little bit just to make it work better for me. And so I'm kind of wondering where it maps, like say 1.5 to. Let's check that. That'll give us an idea of the window size. So 1.5. Yeah, it goes down to negative 13. So let's do the following. You can see that if I go out to negative 3 on the x-axis, that looks like I'm going to have most of it there. And then on the positive side, I'll go out to 4, and then I'll go down to negative 15, and that should be good. So we'll go negative 3 to 4. Scale of 1 is fine. We were saying negative 15, and that should get us the local extrema down there. And it all looks pretty good. The only other thing I might adjust would be something like that. That's not a good choice. 5 is a good choice. So here's our graph, and that's a good view of the polynomial. So I'm looking at this, and I'm noticing a couple of things. It looks like I have a root at negative 1. Let's verify that. That is indeed a root. Now there's a fractional root in between negative 1 and 0. And I'm thinking rational zeros theorem, 2 over 6. The constant term is 2 and the leading coefficient is 6. So that could be negative 1/3. That's probably worth to check. So I'll put in negative 1/3 and see what it says. That is another 0. That's very good. And then it looks like I have another 0, and if I had to guess, I would say it looks like it's about 1/2. It's always hard to read fractions off of a graph, but it's worth to check that. So I'll put in 1/2 as well. And that is another 0. That's very good. And then it looks like we have another 0 at 2. And so I think we can check that as well. Let's just put in 2 and see what happens. and that is another 0. So that looks like this polynomial here has all real zeros. That's great. It's a 4th degree, and so we know that we're looking for 4 different zeros, and it looks like each of these has a multiplicity of 1. And so I pretty much can avoid the synthetic division here. I think that I should be okay. It looks to me like I would have as follows. So we want to make a notation here to indicate that we graphed it on screen. And we had a root at -1. We had another root at -1/3. We had another one at 1/2. And we had another one at 2. And so if we start this as follows. Now, one thing that is confusing to a lot of folks, let's go back to the iPad screen. I didn't realize I hadn't switched yet. There we go. So you can see I recorded those roots that we found. And they're asking me to basically present this in factored form. And so now that we know what the roots are, we're in pretty good shape, and we could probably just do the following. You can see that the leading coefficient is 6, and so you can pull that out if you want. It's fine to leave it out. But we have a root at -1, so that would be x plus 1. We have another root at -1/3, and so that would be x plus 1/3. We have a root at 1/2, so that would be x minus 1/2. And we have a root at 2, and that would be x minus 2. I guess I should wall that off a little bit there like that. Now, your learning management system may not be wild about having that particular version of the answer. So you can kind of clean that up a little bit, because you understand that 6 is 2 times 3. And so if you have x plus 1 and x plus 1/3 and x minus 1/2 and x minus 2, you can kind of selectively distribute those factors. You can distribute the 3 across that quantity right there, and you can distribute the 2 across that quantity right there to make a much cleaner version of the answer. And so I would say a good answer would be as follows: x plus 1. When you multiply that quantity x plus 1/3 by 3, you're going to get 3x plus 1. Likewise, when you multiply the quantity x minus 1/2 by 2, you're going to get 2x minus 1. And so that's a very reasonable teardown of that particular polynomial. And this is in general what we're asking for. You know, we are going to give you a polynomial, and our expectation is that you would be able to obtain the roots of that along with the associated multiplicities. And so I do have that here. And by the way, if you want to be super clear about this one, you could say something like the following. So we said that we have a root at -1, and that has a multiplicity of 1. We had another root at -1/3, and that has a multiplicity of 1. And we had a root at 1/2, and that has a multiplicity of 1. And then we have a root at 2, and that has a multiplicity of 1. And so you can see that altogether, when you add up the multiplicities, you get 4, which is the degree of this polynomial. So if you're feeling like that's something you can do, I would say, well, hey, check it out. We got another example right in front of you here. Give it a shot. See how you do. Here's what's next. It's a 6th degree polynomial. And if you're feeling confident, you could pause the video and see what you can come up with. This is a very nice example. In order to save some time, I already keyed it into my calculator. So let's take a quick look at the graph and see what we can see. I have my polynomial there, and I think that I'll just start with a standard zoom. That pretty much looks like a 6th degree polynomial. Now, sometimes people feel compelled to resize the window, which, that's fine. If you'll notice, though, it looks like it has a global extrema somewhere around negative 1.5. And when you put that value in, you can see that it's all the way down there at negative 238 and change. So I don't think it would be wise to open up the window wide enough to see that. I don't really think you gain anything by seeing that extrema. It's going to make the roots very, very hard to read. So instead of doing that, what I would prefer to do is to tighten up the window a little bit so I can see the roots more clearly, and then we can check the values. So I think I'm going to go like negative 4 on that side, and I'll go positive 4 as well. And that should be sufficient. Let's see how that looks. That's about right. So I can see what appears to be 3 separate candidates for roots. One of them looks to be at negative 3. Let's verify that. And it is. Another one looks like it's at positive 1/2. It is always tricky to read fractions, but that's why we have a calculator. And so I'm going to put in 1/2 and see what that kicks out. And that is a root as well. And those two roots, at negative 3 and at positive 1/2, they both have odd multiplicity, clearly. But that next root, which looks like it's at x is 2, that looks like it has even multiplicity. So let's jot down what we have found here. So we graph this. And we have roots at negative 3, positive 1/2, and 2. And the root at 2 has even multiplicity. So usually if you're going to be doing synthetic division, which we are going to be doing here, it's the most efficient to start with the root that has multiplicity, or if you have multiple roots with multiplicity, pick one of them and start with that. That is going to give you the quickest breakdown and the most amount of traction in terms of getting into what this polynomial is. So I'm going to start off with the root at 2. And when you do synthetic division, my writing style for this may not look like what you have in your text. I've seen many different styles of writing this over the years, and so, I'm not a thought policeman. I really don't care how you write it, as long as you can communicate it coherently, and, obviously as long as you can do it correctly. That's the most important thing. So when you're given a root, you don't have to sweat changing the sign of that when you put it into the divisor box. If you're given a factor, you're going to change the sign on the constant term from that factor when you put it into the divisor box. But when you're given a root like this, you just drop the root straight in. You don't have to worry about changing the sign. So coefficients would be as follows. I have 2x to the 6th, negative 3x to the 5th, negative 13x to the 4th, 29x cubed, negative 27x squared, 32, positive 32, and negative 12. Let's go with that. Bring down the first value. So 2 times 2 is 4. Negative 3 and 4 would be positive 1. 2 times 1 is 2. Negative 13 plus 2 is negative 11. 2 times negative 11 is negative 22. 29 and negative 22 is positive 7. 2 times 7 is 14. Negative 27 and 14 is negative 13. 2 times negative 13 is negative 26. 32 and negative 26 is 6. 2 times 6 is 12. And negative 12 and 12 goes away as expected. So that's synthetic division, and that number at the far right there, the 0, that's our remainder. And so if you review what the remainder theorem says and what the factor theorem says, that shouldn't be a surprise that we got a 0 for the remainder. That means that 2 is a factor, or x minus 2 is a factor. Now, you could report out if you wanted to right now, but it's kind of a waste. it's a waste of time because it really doesn't serve any purpose except to, I mean, if you want to restate the obvious, that would be okay. So what we are saying is that at this point we know that P of x is equal to x minus 2. And when you build your answer here, you're going to go from right to left. So in other words, this would be x to the 0, x to the first, x squared, x cubed, x to the fourth, and x to the fifth. And so you're going to have 2x to the fifth plus x to the fourth minus 11x cubed plus 7x squared minus 13x plus 6. And that's great, but I mean, we still have a lot of division left to do, and so that's why we're saying it's kind of a waste of time to report that, right? I mean, obviously we're trying to be clear here, so I don't mind to take the time, but anyway, normally I would not do that. What I'm going to do, because I know from looking at the graph that root at 2 has even multiplicity, so I want to keep pushing it to find out, well, how much multiplicity does it have? Is it 2 or is it 4? I don't know. So I'm going to keep on dividing. So I'm going to divide another round by 2, and we'll see what we get. So bring down the first number. 2 times 2 would be 4. 1 and 4 would be 5. 2 times 5 is 10. Negative 11 plus 10 is negative 1. 2 times negative 1 is negative 2. 7 plus negative 2 is positive 5. 2 times 5 is 10. Negative 13 plus 10 is negative 3. 2 times negative 3 is negative 6. And 6 and negative 6 goes away. So again, I could report out, but hey, what's the point? Let's do one more round of division to see if the multiplicity is higher than 2, right? We saw it was even multiplicity, but we don't know whether it's 2 or whether it's 4. Hopefully it's 4. That would be great. So another round of division here. Bring down the 2. 2 times 2 is 4. 5 and 4 is 9. That's not good. 2 times 9 is 18. Negative 1 and 18 is 17. 2 times 17 is 34. 5 and 34 would be 39. And that's not good. 2 times 39, that's going to be 90 and 27. That's like 117. So negative 3 in that is going to give me positive 114. And when I get a non-zero remainder like that, what that tells me is that, well, the multiplicity of 2, or the multiplicity of the root at 2 is 2, because I didn't keep on getting even division, right? So that is a signal to me that I need to switch to a different root and see what I can come up with. So now I kind of have to report, just for the sake of clarity. So what I have now is that P of x is going to be equal to x minus 2 quantity squared, right? Because we found out that the multiplicity of 2, we found out that the multiplicity of the root at 2 is 2. And then as far as the rest of it is concerned, I'm going to have 2x to the 4th power plus 5x cubed minus x squared plus 5x minus 3. And that's as far as I can go with the root at 2. So now I'm going to switch to a different one, and my preference would be negative 3. When you have a fraction and you're running a fraction through a synthetic division array, sometimes you get a mess. And so I usually save that for last. Got to do what you got to do. But anyway, that's my preference. So I'm going to start another round of synthetic division right here. I'm going to take the root at negative 3, and I'm going to divide that into the quotient that I got right here, the last one where I had even division. And so I'm going to have 2, 5, negative 1, 5, negative 3. Looks like I'm probably going to need some more space here. And what have I got? bring down the 2. Negative 3 times 2 is negative 6. 5 and negative 6 is negative 1. Negative 3 times negative 1 is positive 3. Negative 1 plus 3 is positive 2. Negative 3 times 2 is negative 6. 5 and negative 6 would be negative 1. Negative 3 times negative 1 is positive 3. And I get even division, which shouldn't be surprising. Okay. Now, when I looked at the graph, if you recall, we saw that the multiplicity of that root there was odd. So it could be 1, it could be 3. Do we want to keep going here? I'm thinking that it's 1. Yeah, I'm thinking that if you look at the way that this polynomial is going to break down, I think it's going to have a total of 4 multiplicity items coming from the real roots, and I think that the final 2 roots are going to be complex. I don't think we're going to get 100% real roots on this one like we did on the last example. So let me pivot to 1/2 now, and we'll see how that works out. So bring down the first number. 1/2 of 2 is 1. Negative 1 and 1 is 0. 1/2 of 0 is 0. 2 and 0 is 2. Boy, that 0 came out kind of ugly there. Let me fix that. Yeah. 1/2 of 2 is 1. Negative 1 and 1 goes away. And that's a good result, because basically what I can tell you right now is if you look at what's remaining, you build your answer. That's x to the 0. That's x to the first. And that's x squared. So I'm in a pretty solid place right now. I think I can cut to the chase and give you an answer. Here's what I found. So we had that root at 2, and we found that the multiplicity was 2. The root at negative 3 has a multiplicity of 1, and the root at 1/2 has a multiplicity of 1. Now what remains is 2x squared plus 2. And that's very easy to factor. I don't even have to worry about using the quadratic formula. But you notice how I have a GCF of 2 right there. And so in order to make my life easier, I'm going to take that GCF of 2. Let me write that neatly there. And I'm going to move it so that it goes into that quantity right there. I'm going to distribute it over that quantity so that I don't have to look at that 1/2. Not that it's the end of the world, but you know, it's just a little bit slicker that way. So in other words, here's what I'm telling you. So I have x minus 2, quantity squared. I have x plus 3. I have 2x minus 1. And then I have x squared plus 1. And I'm happy about that because x squared plus 1 is really easy to factor. If you go back and look at a couple of other videos in the series, you can actually treat that using the difference of squares pattern, and the roots end up being plus or minus I. You could use quadratic formula if you want as well, but it's kind of like, you know, I mean, if you're reasonably skilled using the difference of squares, you know, insisting on using the quadratic formula for that is kind of like trying to eat soup with a fork or something. You know, it's a lot of work for not much in the way of results. So I'm going to cut to the chase. Here's my final factored version of this. I'm going to have x minus 2, quantity squared, x plus 3, 2x minus 1, and then that quantity right there factors as x plus I and x minus I, difference of squares. And so at that point I have my factors. And if you asked me, you know, hey, what are you telling me exactly? I'd say, well, here's what I've got. In terms of roots and multiplicity, I have a root at 2, and that has a multiplicity of 2. I have a root at -3, and that has a multiplicity of 1. I'm going to need a little bit more space there. I have another root at 1/2, and that has a multiplicity of 1. And then I have roots at plus or minus I, and that has a multiplicity of 1 each. So if you're keeping a tally, 2 plus 1 plus 1 plus 2 is 6, isn't it? And of course this was a 6th degree polynomial. So we have all those roots and we have their multiplicities. Stay tuned for the next video.